Now that we have established that there is a relationship between the natural logarithm and the definite integral, it's time to go ahead and look at the official definition now of the natural logarithm using the definite integral. So provided two very important things. Number one, we're dealing with real numbers, provided that x is a real number and x is a positive real number. X is greater than 0. Sometimes you'll see x is an element of r plus, and that's a way of saying both things. If that's the case, then we can actually define the natural logarithm of x to be the definite integral from 1 to x of 1 over t dt. Remember, we need a dummy variable to integrate, so we typically choose t. Also, sometimes this is written as the definite integral from 1 to x of t to the negative 1 dt, which is just using our negative power there. Therefore, I could define the natural logarithm of 3 as the definite integral from 1 to 3 of 1 over t dt. Now, let's take a moment and let's approximate the natural logarithm of 3 numerically. Remember, in a previous lesson, we had to know how to take a definite integral and transform it back into a Riemann sum approximation. That's a skill you have to have. The majority of functions, the vast majority of functions and models in the sciences are not directly integrable by hand, and you've got to use some kind of numerical approximation method. So we're going to do that now with the natural logarithm. So we're going to take this integral of 1 to 3 of 1 over t dt, and we're going to transform it back into a midpoint approximation using a Riemann sum, acknowledging that the answer we get will not be the exact value, but will be an approximation to that value. Okay? We're going to let n equal 10. The interval is from 1 to 3, so delta x immediately becomes 1/5, b minus a over n. xi star, using the formula for midpoint, becomes 1 plus 2i minus 1 over 10. Okay, let's proceed from here. Now, transforming the definite integral into the approximation, this part right here should not say equals. I apologize for that. This here should be an approximation symbol. I'm going to fix that later. So not equals, but an approximation symbol. The sum of the function, this is the height of the rectangle times the width of the rectangle. Distribute the 5, we get the following, and then summation of this expression, which means we get 1.09714 as the Riemann sum approximation. Computing the relative error, which is the percentage by which we're off. Natural log 3 minus our approximate value divided by natural log 3. That's not too bad. 1.34 times 10 to the negative 3 is the percentage that we're off. So that's pretty good. Let's talk about differentiability and continuity of natural logarithm and e to the x. Way back when we began to differentiate ln of x, we did that by assumption. We didn't prove that the natural log was actually differentiable. We assumed it was. But now we have the second part of the fundamental theorem of calculus. Guess what? Haha! We can now say, well, we assumed it true, but now we know it's true, right? So back in the day, we proved that the derivative of the natural log was 1 over x, provided that x was larger than 0. However, we now have our integral definition of the natural log, 1 to x of 1 over t dt. And the second part of the fundamental theorem of calculus comes into play. Now, since differentiable functions are themselves continuous, this immediately shows that the natural log of x is continuous and differentiable for x greater than 0. Okay, what about e to the x? Well, as wacky as it sounds, we can take e to the x and define it in terms of a natural logarithm. E to the x is the same as the natural log of e to the ex, e to the x. But that's the integral from 1 to e to the x of 1 over t dt. Therefore, by the same reasoning above, e to the x is continuous and differentiable. Turns out e to the x is always greater than 0 for every x in the real number line. And so that means e to the x is both differentiable and continuous on the entire real line. And there we go. So this concludes the second part of our lesson. What have we talked about? We've talked about the actual definition of the natural logarithm using the definite integral. We've talked about approximating the natural logarithm numerically with a Riemann sum. That's a skill you can't let go to waste. You've got to make sure you understand that. And we've talked about how do we know that natural log and e⁻ really are continuous and differentiable. So that's been this part of the lesson. All right, God bless you wherever you are today.